Welcome to another wonderful Calculus 3 day, and we are going to continue our study of line integrals. Recall last time we did our very first type of line integral, which is known as a scalar line integral because you're integrating a scalar function, typically a density function, because usually those line integrals are used to find the mass of a wire. The next two types we're going to look at today both have to do with vector fields, okay? So this next one, I call it type 2. The book doesn't call it type 2, okay? This is Professor Rasky talk, okay? But the application is it's used to find the work done by a force field on an object as it moves through the field. Now, I call this the FDR version, and again, you won't find this in a textbook. You'll see in a moment why I call it the FDR version. It has nothing to do with FDR, the president with the initials FDR, Franklin Delano Roosevelt. So let's first do some prep work and some review. So recall in the very first chapter we did this semester, we talked about work. Yeah, and this is a physics concept. So work, which we'll call W, is equal to force times distance, where you've got some constant force acting on an object. And this is the type of formula you use when the force is acting along the line of motion. And usually you're not that lucky, okay? If you are that lucky, then work is going to be equal to the magnitude of the force times the distance, which is going to be PQ. So I'll do that little granite piece that I did from the very first time we saw this. So let's say you have a big piece of granite and you pull it with some force, and let's say it ends up over here at Q. So the distance is the distance between P and Q, and if you formed the vector PQ, it would be the magnitude of PQ. Okay, so that's work. But this formula only works if F acts along the line of motion. So it's pointing in the same direction as the vector of the PQ vector. And usually that's not the case. You're usually never this lucky. So usually we don't use that formula because we don't have all the criteria for it. So what's the more usual type of work formula? So let's say again, we have the big piece of rock. Only this time, let's say your rope that you've tied the rock, you're pulling, but a little bit at an angle with the horizontal. And let's say the angle you're making here is theta with the horizontal. That's a theta. And let's say your rock still ends up over here at the point Q. Then your work is going to be the part of the force that is acting in the line of motion, which is the projection. This blue vector I have here is the projection of F onto PQ. Okay, so your work is going to be the magnitude of the projection of F onto PQ, and then times the distance, and the distance will still be the magnitude of the vector PQ. And this is more usually used, but even more than that, and we talked about, if we make a right triangle here, it turns out that this work formula is the same as cos theta, the product of the magnitudes. Okay, and that's the same as F dot PQ. And this is key right here. And so I hope you remember some of these formulas from the first module. So these two formulas here are the typical formulas we use for work. Well, which one is better? The one with the cosine or the one with the dot product? It depends on the information they give you. So, pick one that's pertinent to the information given. But in this particular module that we're discussing line integrals, the one I'd like you to focus on is the dot product version, because that's the one that's going to show up here or something like it in our line integral. So here's some pictures here, some diagrams. Let's say you have a vector field, and you know vector fields now are collections of vectors. Could be a velocity field like, wind blowing, or water velocity swirling around, or maybe it's a gravitational field, or maybe it's an electromagnetic field. Whatever the field is, let's say you've got an object moving along this curve right here. See, what is the work done by the vector field on that object as it's tooling along the curve? Well, remember this big T, the unit tangent vector? Sure you do. We studied big T a couple months ago. So remember, big T is the unitized velocity vector for the vector valued function representing the curve. And you know that the vector T is always going to be tangent to your curve. So you could, draw a bunch of T's along here as the curve swirls around. And it turns out that these force vectors from your vector field, you want to project them onto the unit tangent vector. And so you remember projection involves a dot product. So F dot T times T is the projection. And then, so if I write this out, projection of F onto the unit tangent vector, I'll do the formula we had. So when you do projections, this is a good review for the final, that's projection of F onto the unit tangent T. It's going to be a scalar multiplied by a vector. And the vector is going to be the unit tangent vector, and the scalar involves the dot product of F and the unit tangent vector all over the magnitude of the unit tangent vector squared, but that's always going to be 1. Well, how come? Because the unit tangent vector's magnitude is 1. And so that's why they write it as F dot T. T, like so. And so there you have that projection. They're talking about it right here. So when you're determining the work done by this force field, you only need to consider the part of the force that's acting in the same direction in which the object is moving. And so a colleague of mine had a really good idea to sort of visualize this. Suppose this curve was like a roller coaster track or something like that. And you were sitting in a little box car and on this ride, it could be a Disneyland ride or maybe Magic Mountain. And let's say you wanted to pull you'd say it was stalled or something, a little car, and you wanted to pull it along the track. Well, the force that you would use to pull the little car along the track, the only force that would matter or actually move that car along this roller coaster track would be the force that you're pulling with that's in the same direction as your track. I mean, you wouldn't want to be pulling it this way, pulling up. I mean, it might move a little bit, okay, because there is some part of that force that's acting in your line of motion. But it'd be more impactful and effective if you pulled along the line of motion, and hence the projection, okay? So, we're going to do the penumbra of a proof here. So any point along your curve, look at your projection, and then on a small subarc of the curve, remember arc length is little s in mathematics. So if we take a subarc, we'll call it delta f sub I. The increment of work is delta w sub I. That's going to be the little bit of work. And that's still going to be force times distance. But for us, that's going to involve the dot product. This force right here is the dot product of the force from the vector field dotted with the unit tangent vector. And this x sub I, y sub I, z sub I is, these are vectors evaluated at a point. And then times, and then the distance here is going to be the little bit of arc length that you're traveling along the track there, delta s sub I, like that. And that's what I want you to fill in the blank right here. Okay, so you're going to put this right here. Dot product, vector field, dot product with unit tangent vector, times little bit of arc length. Little bit of arc length. Just a tiny bit. Okay, so how do you get the total work? Well, you do a Riemann sum, add it up, take a limit, that whole thing. And so your work ends up being a line integral. How do you know it's a line integral, not a regular integral? You're going to put a C down below the integral symbol. So here's your integral symbol like this. And when you see a C down here, that's the quick way to tell, oh, that's a line integral. So you're going to have your vector field evaluated at some point, x, y, z, dot product with your unit tangent vector, big T, and then your arc length element is ds. This is the arc length element. I'm going to keep calling it these so you get the vocabulary. So if I clean this up just a little bit to make it less awkward, let's just sort of get rid of the XYZ part so it's a little more streamlined. So make it look like that, F dot T ds. Now let's use our knowledge of big T. What do we know about big T? Well, he is the unitized velocity vector. So I'm just replacing big T with the definition. It's r prime divided by the magnitude of r prime. Okay. And then what about the little arc length element? And we learned about the arc length a couple times now. And that arc length element is the magnitude of velocity, basically speed, dt. And now we simplify this. We're going to reduce this to lowest terms. Well, what do you mean? The magnitude of r prime cancels. And so what do we have left? Well, we're getting there. We're getting somewhere. So what we have left is we still have a line integral. We have f dotted with this r prime. I'm going to rewrite r prime with more of the differential notation dr dt. And then we still have this dt over here, like that. And then these dt's you can think of as canceling. Aha! And then what are you left with? The vector field dot product with the velocity vector. And this is why I call it the FDR line integral. You can see why now, FDR, ha ha ha. Okay, now let's do the official definition. So you've seen it all. You've got a continuous vector field F defined on a smooth curve C given by a vector valued function R of t. And by the way, if they don't give you the R of t, you may have to parameterize to get it. So I just put a little side note here. You may have to parameterize to get this if it's not given to you outright. And you will have to also figure out the range of your time t when you're parameterizing. But if they give it to you outright, it's like, hey, you made my life easier. Then the line integral of f on c is given by line integral. You put a c down below your integral symbol, f dot dr. And this is the one that we're going to use. And then this definition, they're just showing backwards how they came up with it. It really came from projecting the force field onto the unit tangent vector, f dot t, and then multiplying that by the arc length. Okay? So that is essentially when you rewrite it as a regular integral. Like, when you get one of these, like, how do you deal with that? Like, well, I can't integrate that. You turn it into a regular integral. Well, how do you do that? And so what you're going to do when you turn it into a regular integral that, you know, a calculus 1 person could do, hopefully, you put your integral symbol, and then you have your time constraint here, your time interval, a to b. And then your force field is evaluated not at x, y, z, but at x of t, y of t, z of t. So you're going to cherry pick the x, y, z components from your vector field and substitute those for your force field. I'm putting arrows here, but that's simplistic. You have to do the right components. And then you're going to dot product that with r prime. And this is a true dot product. I mean, for reals. You know how to do a dot product because we did that at the very beginning of the semester. So now we're going to do our very first example of doing this type 2 line integral, which I call the FDR line integral. And it's pretty cool, and it's not that hard. Okay, so this one that I'm going to do here is sort of easy because they gave you most everything on a silver platter. Not everything, though. So what did they not give us? We're going to find out. So they want us to find the work done by a force field on a particle as it moves along a helix given by r of t equals cos t sine t. And they're telling us from the point 1, 0, 0 and finishing at the point negative 1, 0, 3 pi. Now, for those of you who don't know what a helix looks like, you know, I want you to see this curve because it's kind of pretty and it's worth taking a look at, you know, I think anyway. So let's whip out some graphing software and graph this vector valued function. So the x component is cosine t, the y component, whoops, is sine t, and the z component is t. And it may only show a bit of it. Yeah, there's a problem because I'm not I got to do my parameters here. So I want to show more of the curve. Show me x going from -10 to +10. Same with the y, please. Same with the z, please. And then have t doing, something similar, something crazy. Oops. Not just 0 to 1. That's boring. Okay, let's see if this takes it now. Ah, there we go. So you can see a helix is kind of cool, like a little squiggle. Also looks like a DNA strand. And so we're starting at some point here and moving along the curve and the helix, and we're finding the work done on the object as it moves through this vector field. Very cute. Okay, back to business. All right, so we've got a picture of her. Now, what's missing here? What's missing is the range of t. So the question is, what is the range of time t? They gave us the position changes. We're starting at the point where the x, y, z coordinates are 1, 0, 0, and we're finishing at -1, 0, 3 pi, but they didn't tell us the t. So that's like, Now, this one's kind of easy. Normally, you'd have to solve 3 equations and 3 unknowns, and it's kind of messy. But this one is kind of a gimme, and I'll show you why. Do you notice that one of the components on this vector valued function is simply t itself? Aha! So what does that mean? Well, since the z component started at 0, that means time t started at 0. And since the z coordinate of the ending position was 3 pi, that must mean that time ends at 3 pi. Okay, you have to be careful because it may not be this easy. Well, what if it wasn't that easy? Well, then you'd have to go cosine t equals 1. What is t at that moment? And it turns out t is 0. And then when you do the finishing, cosine t equals -1, when is that happening? Well, there's multiple answers there. So that's a little tricky because it could be pi, but they're saying it's 3 pi. So you have to be a little careful here and make sure that all the components match up with your starting and ending coordinates. Okay, so luckily we got kind of easy peasy here. We got our time. So while we're here, let's get our prime. Well, how come? Well, because we're going to have to take a dot product between the vector field and the velocity vector. That's why they call it FDR. The DR means the derivative of R. Oh, okay. So here's our prime, or R. They gave us cos t, sine t, t, and so the derivatives are respectively negative sine, cos, and 1. Fine. So the work done, which we can denote as W, is a line integral f dot dr. And so what we're going to look at here is we're going to do the, turn it into a regular integral. The time is 0 to 3 pi. So we're going to go 0 to 3 pi. Okay. And then you're going to take a dot product of 2 vectors. So I'm going to cue it up here. And this is where you got to be careful that you don't blow this. It's going to be dt. We already know the velocity vector. So we've got the minus sign, the cos, and the 1. Now, what you got to be careful here. I'm going to show you what not to do. So don't write this down. You want the vector field, but the vector field is -1/2 x, -1/2 y, 1/4. But you don't want to write that. No, 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 no. Ooh, why not? Oh, now I got to erase. Oops, hope you weren't taking notes in pen. No, because I don't want x's, y's, and z's in this line integral. When I convert this line integral, I need it to only have the parameter t. That's it. That's the only variable I should see. Oh, so what do I write instead of -1/2 x? I write -1/2 times the x component from the original vector valued function. Oh, okay. So cos t, comma. Then we're going to have -1/2 y. Ooh, so we're going to write -1/2 times the y component. You replace y with the y component from the curve vector valued function. And then simply 1/4. Okay, so 1/4 is just 1/4. And now we're going to do the dot product. Okay. So now you guys all know how to do dot products. And I want to see all of these steps in slow motion. I know a lot of you like to skip steps. And I'm still going to continue to take points away if you skip steps. I can't even do this in my head. Come on now. So you're going to write down -1/2 cos t times this other x component, negative sine t, plus, and now you'll take the product of the y components. Okay, good to go, good to go. Plus, and then you'll take the product of the z components. And then after we figure out what this mess is, we'll integrate it with respect to t. Now, something is going to happen in this particular example that doesn't always happen. But we actually can simplify this expression. Well, how come? Because this first term, a negative times a negative, is a positive, 1/2 cos t sine t. And when you add that to -1/2 sine t cos t, those add to 0. But don't get too excited. That doesn't always happen. Okay. It did on this easy peasy first example. And now we have the 1/4. And that's really easy to integrate with respect to t. It's just going to be 1/4 t. And then our final answer will be 1/4 times 3 pi, or 3 pi fourths. Now remember, work done can be positive, negative, or 0. So any of those three answers are possible when you're doing one of these work line integrals. Okay. So example 4, effects of orientation. And then there's a yes. Ooh, what does that mean? The orientation will affect the answer. Orientation is the direction that the path is going. And you denote that with an arrow when you graph one of these vector valued function curves. Now, does parameterization affect your final answer? Nope. And remember, parameterization is not unique. We've learned that multiple times this semester. So if you parameterize your curve differently from me, and we both do a line integral together, as long as the parameterizations are legit, they have to match the curve exactly, then our final answer for the line integral should be equivalent. Good to know. Orientation, though, different story. So let's take a look at these two examples on this page. We're going to evaluate FDR. That's the line integral with the dot product of the force field with the velocity vector along a couple of different curves. So the first curve for letter A, they're calling it C1, is given by this parameterization. And you can easily go to your calculator and draw these up. You just go into parametric mode and you make sure that your T minimum and T maximum are 0 and 3 respectively. So you can easily go do this. I'm going to make sure that I'm in parametric mode. Oh, yes, I am in parametric mode. Fantastic. Then I go into y equals, and the x is 4 minus, and I want to delete that. Delete that. 4 minus, whoa. Let's see, 4 minus t. See if I may have to do a clear here. It's not letting me. 4 minus t. Okay, there we go. And then the y component is 4t minus t squared. Okay, cool. Go to your window. They only want t going from 0 seconds up to 3 seconds for this particular line integral. And then graph it. Hopefully everything works out. There we go. So it's a little piece of a downward facing parabola. Okay, very cute. So it's going to look something like that. Oh, something like that. Okay, you're ending at the point 1, 3. And when time t equals 0, you're starting at the, when you plug 0 into this, the position is going to be 4, 0. And it's going in this direction. Okay, that's the orientation. Okay, so we're going to do a line integral on that curve. And we're not going to graph this vector field, but if we did, you could imagine, you know, be some collection of vectors, you know, maybe a jacuzzi. Oh, heck, let's just graph it. I want to know. Inquiring minds want to know. What does that vector field look like? Heck, it could be kind of fun. So if we get rid of this, this is a 2D vector field. So I'm going to go drop it down to 2D. 2 dimensions. Okay, so the first component of the vector field is y, and the second component is x squared. And remember, vector fields look like collections of arrows, a whole bunch of arrows representing like wind or something. Okay, let's see what we got here. Whoa, that doesn't look very interesting. Yeah, not that great. Yeah, let's change color. Blue. it looks like when you get further away from the origin, the magnitude of these vectors from the vector field get larger. That's for sure. That's kind of a look or a flavor. Interesting. But when you're kind of close to the origin, they're pretty short, little teeny tiny vectors. So it's not much going on here. Okay. But that just kind of gives you an idea. So cool beans. So back to where we were. So, you know, if I were to draw the vector field, you know, here, I guess I would draw a bunch of little arrows like, you know, stuff like that. So we've got some vector field here, and this object is moving through the vector field. So how much work is being done on it? Okay, let's go get R prime first, because we're going to need it, because that's what the dr stands for. Get that derivative of the r. Okay, well, the derivative of 4 minus t is -1. The derivative of 4t minus t squared is 4 minus 2t. Fine. Okay, so then the line integral, we'll call it C1 f dot dr, will look like a regular integral going from 0 to 3. You got to take a dot product. So I'm going to cue it up here. Two vectors, dot product. We know that this vector here is the velocity vector. Now remember, the force field, you're not allowed to put yx squared. No, 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 no. I don't want to see any x's or y's. Okay, so what do we put instead of the yx squared? Well, instead of the y, you're going to substitute the y from the original vector valued function, which is 4t minus t squared. And then instead of x squared, you're going to do something squared, but the something is going to be the x component that you cherry pick off of your vector valued function. Oh man, this is going to look terrible. Ugh. Okay, let's keep going. Take a dot product. Okay, so you're going to take the dot product. You're going to do the product of the x components, yeah, plus the product of the y components. This whole mess. dt. Ugh. Now, I don't feel like doing this, okay? I'm really tired. So go use your graphing calculator. You know, this is just a single integral. I'm just going to put et cetera, you know, integrate it. And the final answer is 69 halves. Okay. And we're done with part A. Yay. What does that mean? It means there's a positive amount of work done on this object as it moves along this curve by that little vector field. Okay, fine. Let's do same vector field now for part B. So we're still going to have this vector field, but we got a different curve, C2. So if you go, okay, well, what's that going to look like? Well, I don't know. You could go to your graphing calculator and graph it for fun. And so this guy, the x component is simply t, and the y component is 4t minus t squared. And then the t minimum this time, they're telling us, is 1. And the t max is 4. Now, don't blink, because this particular path has something in common with the other path, but then there's a little something different. So watch yourself here. Okay, I'm going to hit graph. Whoa, it went pretty quick. It's kind of hard to see. But I claim it went in the reverse direction. It's actually the same curve, but the opposite orientation. Ooh. Mm-hmm. So it started here at 3,1, and then it went boom, and it ends over here at 4,0. Okay, so same curve, opposite orientation. Okay, no worries. Let's do R2 prime. So I'm just getting the velocity vector here, no worries. And then the FDR, I'll call it C2. Oops, that's not very nice here. Let me try that later. C2, F dot dr is going to become the integral going from 1 second to 4 seconds. I'm going to have to take a dot product here. The R prime is going to be there. And now remember, it's the same force field, but you got to be careful. And you're not going to put the yx squared. You're going to grab the y from the new vector value parameterization. And then x squared, the x is just t. So you have t squared for that second field's component. And then take a dot product. Okay, so we're going to multiply 4t minus t squared times 1. Oh, that's easy. Plus this guy here, t squared times this y component, that guy there. and then integrate with respect to time. And once again, I don't feel like doing this. You can go ahead and do it. Don't forget to distribute this t squared. I'll just put et cetera, et cetera, et cetera. Pretty easy integral to do. Any self-respecting Calc 1 student who can do it. And I get, negative 69 halves. Can you get a negative work done? Absolutely. You can get positive, negative, or zero when you're doing one of these work line integrals. So what is the moral of the story, for example, for? The moral of the story is the orientation or the direction that your curve is moving will affect your outcome. If you do it one way, it'll be opposite in sign from the other way. Parameterization, no. We parameterize the curve in a couple different ways here. It's the same curve. The parameterization doesn't affect, like, as long as the parameterization is legit. Okay, so are you guys ready to try one? And for you folks watching at home, write this down. It's not in your course reader, and just try it. So I'm going to have you guys work on a little problem. Write this down. You're going to evaluate this line integral, f dot dr, see, where your vector field f, x, y, z, is going to be this vector with components x, y, comma, x, z, comma, y, z. Ooh, interesting vector field, huh? And the curve is going to be given by this parameterization. R of t is going to be t comma t squared comma 2t, where time is going to be ranging between 0 and 1 seconds. Okay, now this is not a hard problem. I picked something relatively easy, but it's just going to give you an opportunity to practice your very first type 2 line integral. Okay, so what the best approach here is immediately go get your r prime, because you're going to need it, right? So your FDR line integral, f dot dr, is going to turn into a regular single integral where the range of t is 0 to 1, and you're going to take the dot product of two vectors. So cue that up. So r prime, we already got that. But then you have your vector field here. So this is your f, but you have to be careful. You don't want to put x's and y's in there. What do? So the xy will become, you steal the x component from your original vector valued curve times y, so that's going to be t squared. So our first component is t squared. Okay, that's weird. And then xz is going to be t, and the z component is 2t. And we'll clean this up a little bit. And then yz will be, I'm running out of room, t squared times 2t. And we got a lot of t's here. So before I do the dot product, if you don't mind, I'm going to clean up my vector valued functions components. So the first component, t times t squared, is t cubed. The second component looks like it's going to be 2t squared. And the last component looks like it'll be 2t cubed. And then I'm going to take a dot product. Okay, so here we go. Here's the dot product now. T cubed times 1, okay, plus 2t squared times 2t, plus 2t cubed times 2. So this big mess, dt. Yeah, well, I'm going to do some simplifying. You've got t cubed plus 4t cubed plus another 4t cubed. Wow, there's a lot of t cubed terms. Why don't we just combine like terms? What the heck? Be a little bit easier on us. So it looks like we're going to have 9 of these t cubed terms. Okay, and now we can integrate. Oh, that's easy. That's just going to be 9/4 t to the 4th, going between 0 and 1, and our final answer is 9/4. Yeah? Everybody okay? So that's just an FDR line integral. Not too hard if the integration isn't hard. Now, of course, somebody could throw in, a problem there where after you do the dot product, you might have to do integration by parts, or maybe you have to use some U substitution there. Who knows? So these are just easy polynomials just to get us warmed up. Okay. So now you're officially done with type 2 line integrals. Congratulations. You're ready for type 3. Okay. So, I guess I did have this in here. I didn't even know. Put it in there. Okay. discusses line integrals is in Calc 1. I've had some students actually do that sometimes. Like I had a student come up to me who was taking pre-calc, and they wanted to ask me, what are all the indeterminate forms in Calculus 2? And I went, why don't you wait till you get to Calculus 2? And they got kind of mad. I thought that was interesting. Okay, type 3, line integral of differential form. Now, here's some good news about this third type of line integral and the last type, because there are only 3 types. It's really the same as type 2. Really? Why do you call it type 3? Because it looks a lot different. And it turns out it looks different because somebody already did the dot product for you. So it's a type 2 where somebody did some work for you already. And they call this differential form. So let's look at sort of why it came from the type 2, okay? So let's say you have a vector field fxy and the components are given by m and n. This is very traditional in math textbooks where your force field, they denote the components m and n. You'll see this when you get to differential equations. And so those are functions themselves. And let's say your vector valued function is given to you by x of t, y of t. Then what does FDR look like, this dot product? Well, if I do this in slow motion, well, okay, let me just tell you what it's going to end up looking like. It's going to end up looking like mdx plus ndy, and that's differential form. Ooh, that's weird. So how does that come about? So let's do this in slow motion. Start with FDR. That's really the dot product of the vector field with dr dt. And so we're going to do this dot product where the vector field has components m and n. And when you take the derivative of the vector valued function here, you're going to have x prime of t and y prime of t for components, and then dt. So now I actually do the dot product. Okay, so you're going to have m times x prime of t plus n times y prime of t dt. But now let's do a little change of notation. You guys all know there's a couple ways to denote x prime of t. One of the ways that's equivalent is dx dt, sure. And similarly for y prime, let's replace it with dy dt, the differential notation. Okay, fine, nothing weird there. And now for the last step, if we treat those differential notations as fractions that we can actually reduce to lowest terms, and we distribute this dt that's out here, the dt's will cancel, and you'll be left with what's known as differential form. So again, the form for a line integral that looks like this, oops, that's a plus, is called differential form. Very important that you know this, because we're going to see a lot of it. A lot. So let's do some differential forms. So, get another meme for you. Put a line integral on a quiz, nobody bats an eye. Make the line integral equal to 0 and everyone loses their minds. Can a line integral equal 0? Sure. Remember, it's denoting work done. And work can be positive, negative, or 0. So it's possible. That's where the meme comes from. So take a look at letter A. We're going to look at a differential form. So somebody already did the dot product for us, as you saw in this little sort of derivation up here. The dot product was done for you, and then they did a little bit of cleanup with different notation. That's all it is. So you don't have to do a dot product when somebody gives you a line integral that's type 3, differential form. The dot product is done for you, but you have to do a lot of substitutions and you have to do them correctly. So that makes it a little tricky. And then this problem, I'm going to jack it up and make it even more difficult because we're not going to parameterize for you. You're going to have to do the parameterization. When I say you, I'll do it for you to start. And that's sometimes one of the tricky parts of a line integral. If you get a nice line integral where they already have a nice vector valued function for you, that means they parameterize for you already. It's like, hey, thanks. But if they just give you information about the curve and they don't give you a vector valued function, you have to do the parameterizing. And it has to match the curve. I had some students a couple years ago they thought that every parameterization was just a straight line. And so they kept parameterizing every curve given with a straight line. It's like, you know, straight lines are nice and everything, but this particular problem here, the curve wasn't a straight line. Sometimes it might be. You have to be careful. So the curve here is a part of a parabola, y equals x squared. Well, what part? You know, you know how to graph y equals x squared. Well, only the portion that begins at 0, 0 and ends at 2, 4. So it's just a piece of it right here. Kind of curvy, kind of nice. So the problem is we have to parameterize before we can even do any line integral, period. Like do the hard work of parameterizing. So first, parameterize, say that fast 3 times, parameterize C. And I already taught you how to parameterize functions of x. Don't act like you don't know what to do. We went over this like 2 months ago. Since this is a function of x, you let x be equal to t. It's that easy. And then since y is x squared, y is t squared. And then stick it all into a vector valued function. So it looks pretty. Got your brackets here. And now you have to figure out what are the start and stop times for time. And it has to match this curve. Well, I'm looking here. If I have to start at 0, 0, it looks like for this parameterization, t squared, if I have t start at 0 seconds, that'll definitely start at the point 0, 0. Yeah. And then if I have time end at 2 seconds, that'll end me up at the point 2, 4. So there you go. My full parameterization is r of t is t squared, and time goes between 0 and 2. So good news. Now, as you know, all of these line integrals that deal with, you know, vector fields and curves, you got to go get r prime. Well, I don't see any r prime. You know, where's r prime in this integral here? The dx and the dy are going to get replaced with the components from your r prime. So that don't skip that step. You still got to go get r prime. Sorry to tell you this. Go get it. Okay. What do I mean? So the dx will get replaced with 1 dt, and then the dy will get replaced with 2t dt. So here, this differential form, I'll just copy it down, is going to become the line integral from time going to 0 to 2. And then you're going to do these terms one by one, x times y times dx. So you're going to go the x component from our vector valued function times the y component of our vector valued function times dx. Well, dx for us is 1 dt. Plus, now the second term of this differential form line integral is x squared dy. So the x component from our vector valued function is t, and you want to square it, times the dy. dy is 2t dt. Now you could integrate these two terms separately. I don't recommend it. Do something, a nice step here. Factor out the dt, just put it out here. And then look what you have here. You've got your first term is t cubed, and your second term is 2t cubed. Let's go ahead and add those like terms together before we integrate. It makes it a little more clean. So we're really integrating 3t cubed, where t goes from 0 to 2. This is easy. You're just going to integrate 3/4 t to the 4th, going from 0 to 2. And then substitute, and then clean this up, reduce. And after that, I get, what do I get? 3 times 16 over 4. And that reduces to 12. And so there is your final answer for letter A. So differential form is really a type 2 line integral where somebody already did the dot product for you. And it does still represent work done on an object as it's moving around in some vector field. Where's the vector field? I don't even see the vector field either. That's a good question. The first term, the thing that's multiplying with the dx, that is the m component for your vector field. It's understood. And then whatever is multiplying with your dy, in this case x squared, that's understood to be the n, or the y component of your vector field. So your vector field, remember, has components m, n. Now our textbook, I think they use PQ, whatever. All right. So now let's try another problem here where it's already parameterized for us. It's like, hey, yay, they did the parameterization. That was awfully nice of them. So what we're going to do here is we're going to just start, getting our prime and doing all the substitutions. So our prime, easy, that's just 2, and then 10. And remember, the 2 is going to take the place of the dx here in that line integral. And then the 10 is going to take the place of the dy. So there's your dx dy. So this line integral is going to become the integral going from 0 to 1. And y minus 3x will be 10t minus 3 times 2t times dx. That's going to be 2 dt plus, and then the second term is x squared dy. So that looks like it's going to be 2t squared. And then the dy is 10 dt. And then I would clean this. I would, again, factor out the dt. And then distribute this 2. What the heck do I have there? No, this is a mess. Let's see. I've got 20t minus 12t plus, looks like 40t squared. Okay. So you can combine these first two terms because that just adds up to 8t. And then if you integrate this pretty easy polynomial, not that hard to do, no fancy integration to worry about. I should get 8t squared over 2 plus 40t cubed over 3. And I'll integrate between 0 and 1. And plug it all in, and I get 52/3. Okay. So we're getting somewhere. Yeah. There's another differential form. We're working up to something soon with these line integrals, and you can see it is somewhat labor intensive to do a line integral. I won't lie, it can be kind of a pain, especially if it's not parameterized already, which we're going to do in the next problem. But I'm going to allow you to do something. Some teachers don't allow you to do what I'm allowing you to do, just so you know. As an engineer, sometimes engineers and mathematicians differ on approaches. Engineers sometimes look for, let's say, a quick way to do something or a shortcut, whereas sometimes mathematicians aren't okay with that. Okay. That being said, I'm going to allow you to do a shortcut if it helps and makes sense. Okay. So I'm going to point out what I'm going to allow you to do in this next example. So pay attention. If you end up taking this class, though, somewhere else, that instructor, and it's their right because they're teaching the class, so you got to go with it however they're going to roll. They may forbid you from doing what I'm going to let you do. So, you can go, well, my other professor let me do, that's not a good argument. Don't use it. Okay, so what is this thing I'm going to let you do? So first, let's look at this next problem. For curves given in 2D, if you have y equals f of x, where x goes from something to something, it's really easy to parameterize the curve because you just let, for functions of x, you just let x be t, and then whatever y is, it's f of t. And then you use time going from a to b because t and x are the same thing. Okay, so you can evaluate the line integral in either x or t. It's going to work out. That's kind of nice. Now, I haven't gotten to the thing that's weird yet, so we're getting there. Yeah. So they're giving us a line integral to go do, and this is differential form. Well, how do I know? Because that has that flavor. It's got something times dx plus something else times dy. So that's the mdx plus ndy flavor. That's differential form. Okay. Now, the curve is given by a parabolic arc. That's just part of a parabola. starting at the point 4, 0, and going to the point 1, 3. And it's kind of going like this. It's sort of going backwards, if you will. So how do I parameterize this curve? So I'm going to let you have time go backwards. Now, other instructors won't do this, okay? You know, the way I'll let you parameterize it is like, hey, function of x, let x be t, and then y will be 4t minus t squared. But here, time is starting at 4 and then finishing at 1. Will this work? I will let you have time going backwards for type 2 and type 3 line integrals only. I will forbid it for type 1 because that's mass of a wire. Okay, so I will allow you to do this for the type 2 and type 3 line integrals. Those are the ones that have to do with vector fields. I'll let you have time going backwards. But keep it going backwards. I mean, once you change lanes, you're going backwards, okay? Now, I want to say something for those of you who, well, I'm a purist, and, you know, and when I look at view an example in MyLab Math, they never let you have time go backwards. So I'm just not going to I'm not going to ever have time go backwards. Okay, fine. We'll still both get the same answer, and my way is easier. Well, what do you mean? I'm going to show you what your parameterization would look like. Remember, parameterizations aren't unique, so yours may look a little bit differently. So an alternate parameterization, if you're like, well, I don't like time going backwards, I'm a purist. Okay, you know, I don't want to argue with purists, all right? Let's say you want your time going forwards. You know, time can't go from 4 seconds to 1 second. Okay, so the way you would do it is you would, you want to start at time, you know, where you want to start at point 4, 0. So you're like, oh man. Really? Yeah. Yeah, this is kind of, like I said, parameterization is not unique. So what can I do? Well, how about if I go like have x, the x component be 4 minus t, because if I'm going to have, let's have t start at 0 seconds, okay? And then since y is equal to 4x minus x squared, y will be 4 times x, but x is 4 minus t, minus x squared. That's kind of a mess, and you can clean that up a little bit if you want to FOIL it out. Okay, that's fine. But I claim if I go to if I finish, where do I want to finish? I want to finish when x is 1. If I finish at time t equals 3 seconds, I think that it'll match this this curve. Okay, so that's an alternate parameterization where time is moving forwards, you know, and everybody's happy if you want your time moving forwards. And I'm okay with it, but it is kind of messy, you see, and you're gonna have to do a little bit of work and clean up, and, you know, if you want to make it look pretty. So I'm not going to use it. Okay, I'm going to use mine where I will allow you to have time go backwards. Now, if you are going to have time going backwards, what that means is that if you're going to evaluate y dx plus x squared dy and turn this into a regular line integral, you're going to start at time at 4 seconds. So the lower limit is going to be larger than the upper limit. Ooh, because you're having time go backwards. Don't flip it, okay? Just leave it. You're fine. And then what? So you're going to replace the y with the y component from your parameterization. So that's 4t minus t squared. And we better go get r prime. All right. So I did this alternate parameterization. I'm going to erase it now because I'm deciding not to use it for this problem. You can if you want. I'm okay with it. I'll give you credit. R prime for me is 1 and 4 minus 2t. So this is the dx. And this right here is the dy when I start doing replacements. So I'm going to have 1, and I'll put the dt way out here so I don't have to factor it out. And then x squared, so the x component for my vector value function is simply t, so t squared. And then my dy is 4 minus 2t. Okay. And then this is pretty easy to integrate. You know, you may want to distribute your t squared. I'll just put et cetera, et cetera. So when you get to, I'll get to the antiderivative after I did the cleanup. Looks like this. Skipping some steps here, but I think you can do some arithmetic and so on. And then integrate. And so here is your antiderivative, and you're going to evaluate it between the limits of 4 and 1. So yeah, plug in your 1 first, because that's the upper limit. Yeah, because you're having time to go backwards. And then minus, and then plug in the lower limit, which I know is larger. That's okay. We decided because that matched our orientation. And then when you do all this, I get, let's see what I finally get, I get 69/2. Okay, and it worked. So that is the correct answer. So there's differential form again, where we had to do the parameterizing. And in order to match the orientation of the curve, we had to have time going backwards because the orientation had the parabola going in this direction. If you did it the opposite direction, then your orientation would have been reversed and you would have gotten negative 69/2, but that's the wrong answer. And I'll know when you messed up with your orientation where it doesn't match what the problem is asking for, because you'll be off by the wrong sign. Okay, so you'll know. Three-dimensional differential form. Oh my God, can you do that? Yes. Sure, why not? We do a lot of stuff in 3D here in Calculus 3. So your vector valued function will have 3 components, and the tradition is having M, N, and P. Unfortunately, the book we're using, I think they use P, Q, and R. Just breaks my heart. But anyway, so you're going to have a vector valued function and some time constraint, hopefully. I'll put like some, oh, what just happened there? And hopefully some time constraint that they give you with that vector valued function. Then the FDR, and we pointed this out already, I'm just doing this in 3D now, is the same as the dot product with the vector field and the velocity vector. So you're going to have your force field given by M and P, and then you're going to have your velocity vector x prime, y prime, z prime, and then times dt. And then when you do all this dot product and then do the canceling with the differential form, you're basically going to end up with the 3D differential form. It's going to have this look to it. Looks almost like the 2-dimensional differential form, except you got one extra term here, the PdZ. Okay. So let's take a look at doing a 3D differential form. And we're going to have to parameterize. But it's an easy parameterization here because it's a straight line. And you know how to do straight line stuff since we studied that in the first module. So here's your 3D differential form, and the M, the N, and the P are understood to be the factor multiplying with the dx is your M, whatever's multiplying with the dy is your N, and your P is multiplying with the dz. Fine. And you remember when you're given 2 points, how you parameterize a line? You know, if this is point P and this is point Q, go get the direction vector PQ, and that's easy here. Terminal minus initial, terminal minus initial. So this is your direction vector for your line. And then if you do the parametric equations, x, y, and z, and you can pick the point 0, 0, 0, you know, that's always, and then these are your direction numbers here, 0 plus 3t, 0 plus 2t, and then just put it into a vector valued function, you know, t, 3t, 2t, and then you have to figure out what are the start and stop times for your time, and you want your curve to start at 0, 0, 0. Aha, then maybe I should have time start at 0 seconds. That'll start me at the point 0, 0, 0. And you want to finish at 1, 3, 2. Well, it looks like if I let t be 1 second, that will stop me at the ending point 1, 3, 2. So here we go. We got the parameterization. Straight lines are always easy to parameterize. It's the curves that can be a little tricky. Okay, let's go get our prime. And for this particular case, it's a constant vector. Nice. So the FDR, which is really this differential form, m dx plus n dy plus p dz, is going to be the regular integral going from 0 to 1. So the m for us was 2xyz. Oh boy, 2xyz. So we're going to have 2, and then the x is t, and then the y, and then the z, and then the dx is basically 1. So this is the dx, this is the dy, this is the dz, plus, and we'll take the dt out. Plus, what's next? The second term is x squared z dy. Oh, so is that an x squared or x cubed? Man, my eyeballs are shot. It's not even Friday yet. X squared z. Okay, so that's going to be t squared z. That's 2t. And then we're going to multiply that by dy, but that's going to involve a 3 dt essentially. Plus, and then the last term for this differential form was x squared times y times dz. So that's going to be t squared, y was 3t, and then the dz was the 2. Okay, and this mess, if you do some multiplying it out, looks like it's going to be a bunch of t cubed terms. Woohoo! And that's like, okay, fine. I'm just going to add up all the t cubed terms. I think I get 24 of them, 24 t cubed. And that's easy to integrate. It's just going to be 6t to the 4th going from 0 to 1. Final answer is 6. Okay, so what's the moral of the story? We are now officially done with 17.2. You now know all the kinds of line integrals out there, as well as the other skill set you're going to need, which is parameterizing curves. Okay, that's important. And I'm going to let you, if it matches the curve and you need to, have your time go backwards, but honor that and stay in that lane if it helps. Okay, sometimes it doesn't help. You want to have time going forward. Just keep it going forward, and that'll match your curve. Okay, so that concludes 17.2. Congratulations.